So ever since we were little, we learned about magnets, and we learned that there's a north pole and a south pole, and the magnetic field runs from north to south, and we get this pattern around a magnetic field, a bar magnet that looks like this. So it's going from north to the south, into the south and out from the north. A small compass is used to establish the direction of the magnetic field at any point near the magnet. You can also put a whole bunch of magnets around there as well. So the other thing as well is that if you are inside the magnetic field runs from south to north. Now we're going to watch a video now about a whole lot of different magnetic fields. What's interesting is it's not only magnets that make magnetic fields, but they're also, if I have an electrical wire that is going with current, let's say going from the positive to the negative, it will also create a magnetic field around that wire. So first we're going to take a look, and if I change the positive and negative, you will notice that the magnetic field changes its direction as well. Take a look at the next scenario. What if I put a current carrying conductor in between two magnets? I notice that the current carrying conductor will move. If I swap my north and south, it will move in the opposite direction. If I swap the direction of the current, it will move in the opposite direction. And we'll talk about the interaction of this magnetic field in a second. What's happening is you've got a magnetic field. I'm just going to draw this slightly differently. If I have a north pole over here and a south pole over here, the magnetic field runs from north to south. And it goes like that. If I have a current carrying conductor, I can show the current coming out the page with a dot that looks a lot like out. And if I'm wanting to show the current in the page, I use a cross, which is the opposite one it's in. You get this circular magnetic field around it, as we spoke about just a sec ago, and it is in a specific direction, which I will explain to you in a second. And if it's going into the page, the magnetic field will be clockwise. If it's coming out of the page, the magnetic field would be anti-clockwise. So in this case, we've got a clockwise magnetic field, and it is inside. Okay, so this current is going into the page, down and into the page over there. And I have got a clockwise motion. So up at the top over here, I have got lots of extra magnetic field. Over here, I have a cancelling out effect. In other words, the magnet is going from left to right, but the current carrying conductor has a magnetic field that is going from right to left. So these cancel each other out. And what happens is this wire experiences a force into that space. We take a look over here. Over here we have got on the right of this thing, there's a lot of magnetic fields. On the left, the magnets are running towards the bottom of the page, but the current carrying conductor has a magnetic field that's going to the top of the page, and as a result, this is being pushed into the space where there's a cancelled out magnetic field. And just taking a look at some of these magnetic fields over here, this is a current carrying conductor. It's going into the page over there. And we have got the circular magnetic field around it. Those are iron filings. Sorry, they shouldn't cross over. All right, so there is a magnetic field about any straight current carrying conductor. This field consists of concentric circles and can be studied using iron filings or small compasses. In this situation to the right here, I have got a current moving from positive to negative, and my current is going into the page. Remember, we've just spoken, if it was going into the page, then I would have a clockwise magnetic field. If conventional current is going into the page. I'm able to work that out by using what is known as the right-hand thumb rule. So the direction of the magnetic field about a straight conductor, clasp the conductor with the right hand, like that, with the thumb pointing in the direction of the conventional current, and the fingers will curl in the direction of the magnetic field. I want you right now to take your right hand and try and stick your thumb as if it was going into the page. And then over here, we're going to try and put our thumbs, out of the page. The dot is out of the page, and the cross is into the page. So stop. Put your right thumb out the page. You will notice that your fingers curl in that direction. If I put my right thumb into the page, you will notice that your fingers curl in that direction. So that's how you work out the direction of a magnetic field about a straight conductor. What if I had two magnetic fields about a straight conductor? Over here, they would start to interact with each other. So the one is going into the page, that's clockwise, out the page, anti-clockwise. Current, we've shown that, okay. And what happens when they interact with each other? Well, in the middle over here, this magnetic field is coming down, and this magnetic field is also coming down. So these two are going to reinforce one another. And what's going to land up happening is you are going to land up with a strong magnetic field in the middle over there. And so that the shape of that magnetic field is going to be a high density of magnetic field lines in the middle. So it will look something like that over there. And therefore, these two wires would push apart from each other. And then over here, if I've got two currents going in the same direction, so if we just pretend for a second, well, let's just draw one out here. I've got an into the page and an into the page. What would happen is I would land up with clockwise, down, clockwise, and this one is going up on that side over there, and we would find that that cancels out, and therefore these two wires would move towards each other. So these magnetic fields cause some sort of movements. So if the currents are in opposite directions, then they are going to move apart, and if the currents are in the same direction, they will move together. And here's a slightly emphasized version of that. So over here, they're in the same direction, and therefore they cancel each other out in the middle, and you land up with them moving together. Here they are in opposite directions, one into the page, one out of the page, and they force each other apart. What about if I had a current carrying coil? We call a current carrying coil a solenoid. It is a coil of wire, and it's just going round and round and round and round and round like that. And what if we had to draw a magnetic field about this coil? And I'm going to show you exactly what happens. Alright, so what I've done is I've basically magnified three of these little wires. The current is coming from the positive into the page and out of the page, and into the page and out of the page and into the page. So I've magnified that, and your wires would kind of be going like that, alright, and your current would be coming out and in. The direction of the magnetic fields is given here, and as you can see all along the top here, all the magnetic fields are going in the same direction, and at the bottom, and inside they are going in exactly the opposite direction. So what you establish is magnetic field lines that look something like that. And if that should ring a bell for you as looking a heck of a lot like a north pole of and a south pole of a magnet. So what happens is if you were to put an iron bar inside the solenoid, it actually magnetizes it, and it lands up that the magnetic field is from north to south on the outside of the bar magnet. So this is an imaginary north pole that you create. And this is an imaginary south pole that you create. So here we've got a slightly more professionally drawn version of it, and my current carrying conductor is going from positive to negative, so it's going around like that. So I do that. What you can do is you can take your right hand and you can coil your fingers over the top, and you will find that your thumb will point in the direction of north, and that is going to be your south. And look what happens to your field lines. They go from north to south, and in the middle from south to north. So let's read this right hand solenoid rule. Clasp the solenoid in your right hand, pointing your curled fingers in the direction of the current flow. The thumb now points to the north pole of the field that has been created around that solenoid. Now, we kind of think metals are magnetic. That is not true. There are only 3 magnetic metals. Iron, nickel, and cobalt are the only 3. Most of the metals we use day to day have got iron in them, and a lot have got nickel and cobalt, so we experience a lot of metals as being magnetic, but those are actually the only 3 magnetic metals. Alloys of these metals are also generally fairly magnetic. An iron nail is in a magnetic field becomes what we call an induced magnet, and that's what I was just talking about in a solenoid. When we remove it, it loses its magnetism, and we call that a soft metal. Steel and alnico are both hard. In other words, if I were to put them into a solenoid, they would remain a magnet forever and ever. Amen. Magnets and electromagnets are used in all sorts of different things. If you change the strength of an electromagnet, you are going to vibrate speakers, and that's how they work. Inside the reading of video material and tape material is all done with magnets and electromagnets, and the microphones and the speakers all use electromagnets as well. An electromagnet, how do we make it? We are going to put a circuit. We put a solenoid around an iron or a steel. Sorry, it has to be iron if you want it to be an electromagnet. And as soon as I turn it off, all of these iron nails over here would fall off. And one of the ways of testing the strength of an electromagnet is to see how many iron nails it could pick up. A simple electromagnet can be made by winding a length of wire about an iron nail and then connecting it to a battery, just like we have here. You can apply the right-hand rule to identify the north and the south poles of the magnet. So what you would have is you would have your current coming in, current comes out over there, so it is going in that direction. You take your right hand, coil it so that the fingers go up and over the top, and you find that your thumb points towards north over there.